So, welcome everyone to the kickoff and the start of this season's for robust optimization webinar. It's an honor and a great pleasure for me to introduce today's speaker. I think Alexander Shapiro does not need any introduction. He's quite well known in the optimization community. He is a professor and a chair at the School of Industrial and System Engineering at Georgia Institute of Technology, so Georgia Tech. He's also a recipient of many awards in optimization community. In 2013, he was awarded the Karchian Prize of Informs for lifetime achievements in optimization. In 2018, he was a recipient of the Danzig Prize by the Mathematical Optimization Society. Um, and applied mathematics. And in 2020, he was elected to the National Academy of Engineering. Of course, in 2021, he was a recipient of the John von Neumann Theory Prize awarded by Inform. This is just a few of his awards. It's a great pleasure and honor having you, Alexander, here. Thank you so much for accepting the invitation to be here. And without further ado, I want to give the screen and the mic to you, and you're all ears to hear your talk.
Thank you very much for inviting me. This is based on work with Yan Li. Okay, so let me start. You know, in the what I would call static formulation, the at least from conceptual point of view, distributionally robust and particularly robust optimization is rather straightforward, right? No, this what the distributionally robust is assumed that one has a certain set of probability distributions, and one take the worst possible probability distribution and minimize that over the set of feasible decisions. Okay. Now there's the big question: how to choose this what they call uncertainty set and so on. In particular, if one choose all possible probability distributions supported on a certain set, that becomes robust optimization. It's because the optimal layer will be attained in a direct measure. Okay, this is now there's many became very popular, many papers and how to do that optimization and all that. Now, the moment we start to talk about sequential decisions, it's becoming non-trivial just to understand what distributionally robust optimization means. And this is what I will try to talk today. It's, of course, it's very much related to risk-averse optimization. Some of you probably know it became very popular of different risk measures. And by dual representation, in some cases, they can be represented with distribution robust and so on. So this is what I will talk today. This from conceptual point of view, and what does it mean to extend distributionally robust to sequential decisions. Historically, from historical point of view, there are three basic models developed by different communities to, let's call it multi-stage stochastic optimization. Okay? There is a stochastic programming community going back to the origins of linear programming and so on. Then there's a optimal control model, and Markov decision processes. Each of these communities went in somewhat different direction of questions they ask, modeling and all that. Of course, it's all connected, but it's not, especially when we start to go to distributionally robust, and this is what I will talk today, it becomes non-trivial. And there's a lot of misunderstanding about that, okay, which I will try to at least to mention. And there's a lot of questions, which I will not to talk today about computational methods. By itself, it's probably a different lecture. What can be done, how to compute that, and all that, it's not trivial at all. Let me start. I will talk about two models. I will talk about optimal control model and the Markov decision processes. Stochastic programming is slightly different. It's more similar to optimal control model. And basically, it has the same questions. So there's, as we'll see, there's essential difference between optimal control model, which is classical, and Markov decision processes. So let me start with some very quick introduction of that. So the stochastic, this is, you can see my slide, right? The stochastic optimal control, discrete time, finite horizon. It's also possible to extend it to infinite horizon. So we have the cost functions, right? And what is important here and what is different from, say, stochastic programming, in this model, there's a clear separation between state and action, or controls, they call it controls there. What is important there, right, to know this, the cost functions there, you can see this. You see this when I call that I do that, look at that, right?
Yes.
Okay. This is a state, this is a control actions, and this is a sequence of random variables, random vectors. Okay? This is important. So what is governed, the dynamics of that is this equation, this functional equation. So given this, there's stages. This here we consider finite number of stages. Given at this state at time t, your action or control that we can try to do, and the realization of random vector, we go to the next state by this functional relation. And there is on this control space. Sometimes it depends on the states. For simplicity, I assume it doesn't depend on states. Sometimes also the initial conditions are supposed to be random, but for simplicity, let's assume this type of model because it's already, main things are already there. Okay. No, this is all these conditions. It should be measurability and all that. Okay. Okay. Let me say this that I will make here is this sequence of random vectors is random vectors independent from stage to stage. This is very important. We will see that. And second assumption that I'll make is the distribution probability measure of that doesn't depend on our action, doesn't depend on state and controls. It's also possible to consider this case when the distribution of that depends on that, but it will be important later. It's very natural, right? This is a random process, and that maybe I mentioned at this point that in stochastic control, this is usually considered as a noise. For noise, it's very natural to assume that from stochastically, it's independent from one stage to the other. But in many applications, it's not really noise. It's realization of the data. This is typically view in stochastic programming. Then the basic assumption that it's independent from one time period to the other is not natural. Imagine this. I don't probably have time. Inventory control, if you know what is that. The demand usually this what happens in this time period, in this month, in previous months, probably autocorrelated. This introduces many additional problems. Okay, okay. This Markov decision process is conceptually somewhat different, right? Again, you see there's a cost functions here. No, this is final cost. This is a cost function here. This is a state, and there is action, which is what before was control. And what is important here, that there is a transition kernel, the conditional probability that if I'm at state st, at time t, and I make the decision about control action at, right, I go to the next state. No, in particular, if this will have no control, it will be just Markov process. If the state space is finite, it will be Markov chain, generally non-homogeneous Markov chain. The stochastic optimal control can be represented as as MDP. The corresponding conditional probabilities, right, of this transition is given just probability. This A is some measurable space. It's defined the probability measure at the state space next time. Okay, but what is essential here, the way how it represented. It's explicitly here defined by this random process, which is in this case is not defined by that. One is and if I want it to be this optimal control, if I want to be this MDP, the assumption that is independent from stage to stage is essential. This then it's really become a Markov decision process, and that. So stochastic control can be considered as a particular case of that. But again, I will come to that later. The way how this probability law is defined, or this dynamics are defined, is somewhat different. Okay, and very often in papers and that they do not distinguish between control and MDP. But as we'll see, right, especially when we look at distributional bias, it's very essential. Okay. Okay. Now, the basic point of all of that is dynamical equations. This is the basis of all of that. Okay. It's possible to write what is called this value function, okay? And they're written in that form. What is written here? Basically, let's look at stochastic optimal control. When we look at stochastic optimal control, what is defined, the stochastic, the law, is the history of random process. Remember, we assume here is that distribution of random process does not depend on our action on state and controls of action. Doesn't depend on that. This distribution doesn't depend on that. So this denotes the history of the process, right? And it's all defined by history of the process. We can, when we write this equation, it is not assumed the stage was independent. It's not assumed that independent from stage to stage. Then, in principle, they depend on the current state and history of the process. From application point of view, first of all, it makes this correspond, as we'll see now. It's not Markov decision process. And in principle, we have to remember all the history. It's made it practically useless. So if we assume this independence, it's simplified. And this is the basis. Okay. In that case, the value functions, this what they call this, or sometimes called Bellman functions, they depend only on state. This is a normal simplification of that compared to that. And the basis is this assumption here. Okay? And this is a dynamical equation. I will not talk today about this numerical methods by itself. It's not a trivial thing. But if I want to apply that for numerics, right, I have to basically somehow to put it in a computer, which could be not trivial. And this is a famous course of dimensionality. Again, I will not talk about that. Now, what is a policy? policy is the just function of the data available at time of decision. At time of the decision, decision maker know the past, we don't know the future, right? And the decisions are made based on that. In this case, what is written here, right, the policy will depend on the whole history of the random process. Okay? The reason for that, it all depends on it doesn't depend on our decision because of this basic assumption that we made. Okay. Here, right, if we assume this condition, the optimal policy, which is given by that, if the minimum will exist, under some condition, the minimum here exists, right? It's simply a mapping from state to action. Okay, this is a normal simplification of that. Okay, this in MDP, right? This it's similar. So we take the expectation with respect to that. And this is integral, it's just expectation with respect to this probability distribution. It depends on state and action. This you see this conditional expectation. This is a different from this is essential difference as we see. The difference is because when here, right, when we take expected value, because of the basic assumption, I don't have to remember my action. It's all defined by the history of the process. And it will be very clear in a few moments. Okay, so let's start next step. So what I said now is some very basics of this decisions, how the decisions are made. Remember, this decisions are sequential, right, based on information that the decision maker has at the moment of the decision. So if I look at the distributionally robust, I try now to extend distributionally robust from static. Static when there is no dynamics. This is just one stage. You have value at this objective function. You minimize that expected value of that or maximum expectation. But here we have dynamics. So it's very natural, right, to say the following. Okay, so I is in control model, and this is easier here. I assume that this true distribution at every moment of this, right? It has marginal distribution because we assume independent from one time period to the other. It has some distribution. No, the classical argument that we don't know the distribution. We take a certain set of possible probability distribution, and we take the most possible case. No, here we minimize, we take the maximum, and we look at that. It looks natural counterpart of this dynamical equation that I showed you here, right? Here we take expected value with respect to probability distribution of that. We take that. The question, what does it mean? You see, the dynamical equations are optimality, in a sense, it's optimality conditions. What problem would that define? This is not obvious at all. If we look at this corresponding MDPs, we have this additional, similar thing. But here, you see that we immediately see the difference, which is not real difference here between these two models. This can be considered as a particular case of MDP, but the difference here is here we directly deal with probability distribution of that, while here we deal with what is called transition kernels. This transition kernels define probability measure of next stage, but it depends on state and action. Here we don't have it. This is given implicitly by this equation. Everything is the probability law completely defined by probability distribution of it. And this is essential. So one thing what I can try to do, it looks natural, right? I say, okay, I have a set of transition kernels, right? Each transition kernel is just this conditional probability. So each element of this set is just one conditional probability, which depends on this, on that and that. This is probably there's probably a lot of confusion of that. This is not a, I will come back to that. But this again, this is a set of transition kernels. Each element of that is just this conditional probability. So the question, in both cases, the question, what does that mean? What problem do they solve? It's not obvious at all. Right? Okay. Now, and here the first confusion that was quite for a long time, and going back to maybe 20 years ago, 25 years ago, this is very basic confusion. In general, right? If I can consider what is called distributionally robust functional, there's no dynamics here, just distributionally robust functional. I have a set of random variables. Random variables is a measurable function on corresponding probability space. And if I put on this corresponding probability space, here I take it for simplicity, finite subset of finite dimensional space, with Borel sigma algebra. We take the maximum of that with respect to a family of probability distribution or probability measures. This is a classical one, okay, in the static case. Now, maybe I'll say it later. It's directly related to what is today called risk measures by duality. I'll talk about that in a moment. So I define I cannot define this type of typically on space of all measurable variables. I need to because of the technical reasons, but usually it's sufficiently large linear space of such functions, which is just random variables. So I can define what is called nested functional. This is well understood now, reasonably well understood in the theory of risk measures. What is you see this is nested. It's going back iteratively going backwards, defined by this composite, which is quite complex construction. If I will take just one of this, right? If I will take just expected value that will be singleton by this total, this is a total, right? Which is a risk measure defined on all this vector of all these histories, it will be just expected value by so-called our probability expectation or expectation, the total expectation. But here it's some complex construction. Now this I defined by this what I defined reasonably well. One can of course there's some technical question. It should be check measurability, some type of the things, right? So it defined iteratively going backwards in time. So at every time period, I have this realization. This is history up to time t minus 1. I look next one, and I take this expectation integral with respect to this, and we take the maximum. This is well, and going backwards in time. And what is very important in this construction is that we assume a certain type of independence of all of this, right, from stage to stage. To generalize that to conditional type of things is very difficult, and if I'll have time, I'll talk about that. And there are some very deep problems with that. But this is a well-defined. Now, what is well known? What is well known now in theory of risk measures, if I can think about that, is this minimizing this. This is a pi is some type of this policies that I have, right? I minimize this nested function. this is how this in risk measures it is defined. It can be defined by, originally it was defined by stochastic control, by stochastic programming models. Basically, the same can be defined for stochastic control models, but this functional is very complicated. It's defined iteratively, going backward in time. If I define it like that, then dynamical equation which I wrote is there. This is a correspond to the dynamical equations which I wrote from the beginning. And this is how it should, this is correspond to this dynamical equation. Okay. If I want to keep this dynamical equation, I have to consider this functional. There is no way out. Okay. And this is a problematic. It's also well known, right, that this will be not equal. This, for example, it will be not equal to this what is called static formulation. When I have what is called risk neutral approach, this will be just usual expectation. This is expected of the total sum. In another case, where it will be the same is robust. Maximum of maximum is maximum. In that case, this nested formulation will be the same as taking just maximal expectation of all of that. But actually, this is only two extreme cases. In all the other cases, it's not the same as consider, say, for example, in his case, and consider this. And this was a big problem. And a lot of misunderstanding of that because it looks natural, right? And maybe I go a little bit ahead. When you go to distributionally robust, and this considers just the maximum with respect to the distribution, which we'll call this static formulation. Okay. Now, one way of dealing with that, okay, is consider that as a game. And this is very essential. And this is actually give completely new understanding of all of that. This game approach to stochastic optimal control is not new. It's going back long way back. Game theory going back 100 years to von Neumann. But this way, I think was not, it's different here because it's not symmetrical. So basically now we have a history of our decision processes. And we consider this as a game between, say, controller and then, say, the nature. Control choose its decision, its controls. Nature choose the probability distribution from the set of probability distribution. I'm talking about control model, which is a set of which is given. And this is a process now. This is a history. This first state that our decision, that nature choose probability. According to this probability, it's going to the next stage according to this functional equation and so on. So this is a whole history of the process. You see now, it depends on our decisions, of our decision of control and of the nature. Nature is assumed to work against us. It will choose this worst possible distribution. So we can write that as in min-max form, as a game between the controller, the decision maker, and the nature. This gamma in the set of possible policies of the nature. Nature is a choose the corresponding probability, and then we formulate that as this type of min-max problem as a game. You see the big step that we made from this what was before. If we do that, right, in a sense, it will be equivalent to the nested formulation, and for that we can write dynamical equation for both. We can write dynamical equation for controller and we can write dynamical equation. I will show that in a moment for the nature. It's all very much related to risk-averse formulations. No, again, I don't have much time to talk over that. I assume that you have at least some idea of what is a modern theory of risk measures. All right. So we can consider that as a certain distributionally robust functionals. All right, and we have some axioms, these whole covariant axioms. What is very important here, that if we want to consider that as a risk measures, again, I don't have much time to go into that, that the set of this probability, there's a basic probability measure, which called reference probability measure, right? And this all is absolutely continuous with respect to that. And the classical example where it is not like that is what is very popular now, Wasserstein, the Wasserstein balls, right? Again, I don't have much time to talk about that. Then it's again, it's this, we have similar things. And they are all very much related to that, because this I consider as a functional. Now, and maybe I mentioned this very quickly, this very important, very interesting point here, right? The dynamical equations which I wrote here, and they correspond to nested formulation or the game formulation. There's a relation between these two. Okay. They optimality conditions. The corresponding policy, the optimal policy is given like that. It's mapping from state to action. Okay, this we consider just dynamical equation. Very often in papers, people just write dynamical equation without thinking or saying what does it mean. One of very interesting point is that generally it's a sufficient condition for optimality and maybe not necessary. What I mean not necessary, because we can consider the general nested formulation. This is stochastic control and stochastic programming is possible to do. So if this corresponding functional distribution is monotone in a certain sense, right? But it could be not strictly monotone. For example, if we look average value at risk, which is very popular now, it has this dual representation, corresponding dual representation, right? That means this is absolutely continuous with respect to that, right? It's not strictly monotone. Okay, it's just a note. Okay. Now, here we have what we call static formulation. It looks very natural. Okay. I'm talking about control. It's easier to talk about control because here all the probability laws define the distribution of all this data vector. Now you have a sequence of random vectors. I can look at them all together as one random vector. They have joint distribution, right? We assume that they're independent from stage to stage. So suppose I put some probability measures on that, and I take maximum of that. And this is looks very natural extension, right? From static formulation when we have just no dynamics, just one state, to multi-stage. Right? I take maximum of that. This is what it's, if I assume that they are this corresponds to stage was independent. Sometimes it's called rectangularity, this type of things. Okay. From what and it was one question, at least for me, it's well understood. It's well understood in the theory of risk measures, for example, which can be considered as distributionally robust, that this formulation is not equivalent to the dynamic formulation that I showed you before, for the reason that I discussed, except in two cases. Except two cases when this it's all probability and it becomes maximum, which is a risk measure, or it's just expected value, just says risk neutral case. In all cases, it's not equivalent in general. Okay, so we have only just inequality between them. This is well, for example, that will not make sense to take this, to take average value at risk of the total sum will be not, certainly not equivalent to taking this dynamical setting. So it was a big question, why in distribution robust MDPs, they can do that in some cases. And this is going back to some well-known papers, maybe more than 20 years ago. Okay. The same question of MDPs. Right? If I look what we call is this static formulation, I take a certain set of the transition kernels, and I take maximum. You see the difference here between game formulation and this formulation. Here we choose this set of this transition kernels before the dynamical process. The state doesn't depend on our actions afterwards. In dynamical setting is a dynamic game between this control making action, right? Nature chooses this probability distribution, and it's going like that. And according to this probability distribution, it moves to the next stage. Here, we choose it a priori. So why they should be equivalent? There is no a priori thing to think about that. Now, so there's no reason a priori why this will be equivalent to this game formulation, because you see the difference. Here, the way how this dynamics introduced is static. Here is dynamic. I don't have much time left, just a few minutes, so let's see. Okay, so this is the same question here when we look at this static formulation distribution of our MDP. So what was invented? We see that this 20 years ago, these two well-known papers, what they call rectangularity. And this was strange for me, right? They basically said that under certain, if we assume certain structure of this set of kernels, of transition kernels, then the static formulation that I showed and dynamics are equivalent. And this was after that was repeated in hundreds of papers, especially in computational papers, because in computational approaches, they solve dynamical equations. So if the static and dynamical formulation are equivalent, one can write corresponding dynamical equation. Why these two equivalent? And this is true. There have been certain type of rectangularity was invented for the certain structure in Markov decision processes of this uncertainty or ambiguity sets of kernels, which give equivalence. And from the point of view of game theory is general, one doesn't need that. But it turns out that in some cases, indeed is equivalent, and it is because the structure of the Markov decision process. In control model that I showed you before, it happens on only very exceptional cases. This was a long question, which at least was not clear to me. And even only this recently, looking that way, I think we start to understand that. I have 3 minutes more, right?
Uh, yeah, I think I would say just 5 minutes.
Okay, so tell me when to stop.
Sure.
Now, we also can consider what is called randomized policies. One of the great discoveries of von Neumann, revolutionary discoveries from von Neumann 100 years ago, in simple game theory, right? That in order to have saddle point, you need to consider randomized policies. Similar thing exists here. What is in risk network case? There's no point to consider randomized policy. It's always will be a set of sometimes they call deterministic policy, or better to say it's non-randomized policy. Randomized policies, we consider the whole distribution. The action is not just deterministic, but this whole, according to you flip the coin and say how you action, right? So what is interesting that the existence of this non-randomized policy is very much related to this existence of the duality. Okay, and the duality is that we can when we write dynamical equation, we can change the min and max. This is a classical in duality theory, right? And when we have this corresponding dual dynamical equations, sometimes there will be no duality gap between these two. So it turns out that this is the condition for existence of non-randomized policies. It's possible to show actually almost necessary and sufficient condition. I have to finish just in 1 minute, so I don't time to go. But it's possible to give conditions, basically necessary and sufficient condition for existence of non-randomized optimal policy. In other words, when there is, we can just restrict our attention to usually non-randomized policy when we make deterministic decision. That was discovered in rectangular sets in some particular cases. No, this is again, by the way, if somebody wants more, right, and there's a couple of recent papers on archive, if someone wants to look more details, there's much more there. I will not have time to go much. I'll have to finish now, but let me say just finally. The basic assumption that when we construct this corresponding nested risk functional, and the control model, this was stage-wise independence. So when we want to go to more complex models, we need computational, this conditional counterparts of distributionally robust functionals. Here, there is no dynamics here. But imagine this, all this sequential formulation based on conditional arguments. So if I say have autocorrelation process, I need to consider conditional functionals. And this is by itself is not clear. There are many questions there. Some progress was made. If somebody interested, we can talk. Okay, I have to finish now.